So let's begin our review of the 2023 Chemistry Regents Part B2 and C. This is what I call the free response section that typically a lot of students have issues with because they have to come up with the answers without a multiple choice. But I want to show you that it's not as scary as some people may think it is or seem to make it out to be, because really, if you've been working on the multiple choice section 1 through 50, these are the same concepts, just hidden behind the blurbs they give. They're just kind of hiding the same concepts within these questions. So if you're working on the same concepts through 1 through 50 in this test, 51 through 85 is the same material, just presented a little differently. And again, a lot of people are intimidated by this. So I hope I can show you that it's really the same concepts and that there isn't no need to be intimidated because you have a reference table and it's the same concept. So let's be crazy and start in order with number 51. Okay, so let's go. So number 51 states that and again, what I will tell you is that they love to give you these blurbs. Okay, so this is a blurb, I always say. And in this blurb, okay, they are providing you with some information that you may or may not need. And that's where I think the intimidation factor comes in. All right. And I say that because, oh my God, I don't remember this, or maybe I do. I don't know the element technetium. I don't know it has several isotopes. I'm not connecting with this question. That's why I will typically say, maybe your teacher disagrees, that you should go directly to the question. So 51 says, compare the energy of an electron in the first shell, all right, of a technetium atom to the energy of an electron in the third shell of the same atom. It has nothing to do with technetium. It has nothing to do. This is a question that is essentially being hidden behind this information. You've seen this question if you spend enough time in multiple choice. What they're just saying to you is, hey, what's the energy of an electron in an outer shell compared to one on the inner shell? That doesn't matter what atom you have. So the concept here is very simple. Okay, I've got myself a nucleus and I'm going to compare shells. So here's an electron in the inner shell, here's an electron that's in the middle shell, and here's an electron in the third shell. And there's something we have seen, if you've been working with me, even on the same test. Electrons that exist in shells farther away have higher energy. They're unstable. And electrons that are closer have lower energy. They are more stable. And you'll say, well, why? Well, electrons that are closer actually feel the positive pulling force. The electrostatic attraction to that nucleus is greater because of proximity. And the electrons that exist in shells farther away, and as you add a new shell, those electrons do physically exist farther away, they, because of distance, because they're farther away from that positive pulling force, which we call the nuclear charge, right? The nuclear charge, all right? They feel the nucleus less and they're easily removed or gained. They're part of bonding, right? So that's important. So all you got to say is the energy in the first shell, okay, is what? Is going to be lower than the atom in the third shell. And that's got nothing to do with the information they gave you. Nothing to do. Really, yes, bright line spectrum has something to do with it because bright line spectrum is talking about the energy released. But the things you have to know is that energy, when electrons move, if they were to move to an outermost shell of an exact energy, they would have to absorb an exact energy value, and they would have to absorb energy, okay, as electrons move away, okay? So absorb, I said about. So absorb energy, and when they do so, they get excited because now they have extra energy. This would be a non-ground state. This system of high energy, and if we were to erase a little bit here, okay, what we're going to find out is there's no electron. There's a lower energy position available. So this electron that has high energy, well, it's going to eventually very quickly leap back to that lower energy position because things in nature move toward low energy. And when they move back to lower energy, they're going to emit energy in the form of light, that bright line spectrum. So that story you have to understand. Electrons, when they jump away from the nucleus that are closer, need energy, and when they jump back, they emit it, and they emit it in the form of light. And that type of light, the type of color given off, we can evaluate in terms of energy. Okay, so that's the part that's important here. All right, so in any case, this question is just saying, hey, the basics of using atomic structure, that the energy level of the first shell is lower. So let's just write that into our answer booklet, because we have to remember that we're not writing our answers into the test. Number 51, electron in the first shell has less energy than electrons in the third shell. And I wrote it that fancy, but you could just say the third shell has greater energy. The electron in the first shell has less. Okay, it's not really about technician, many ways to say it, but definitely the first shell, being closer, has less energy than the third, who is farther away. Electrons are able to, move more and do things because they're not affected. But in any case, on to number 52. Number 52. State in terms of protons and neutrons. Remember, really important to answer your question, okay, as they are directing you to. So remember, answer this in terms of protons and neutrons. Why various nuclides of technetium are isotopes. You've got to know your isotopes. Okay, now again, they have a blurb here, but it's really about isotopes. Why do various nucleotides of technetium or any other element, okay, have isotopes? What are isotopes? Isotopes are the same element, same protons, different number of neutrons. I don't know how else to say it. You need to know that. Okay, so in terms of protons and neutrons, technetium has different forms of the same type of element. So technetium is technetium because it has the same number of protons. What makes technetium or any atom unique to another is its proton number, is its, I had a teacher I worked with, Mr. Buckle, used to say that protons are the social security number of each atom. A really good way of remembering that. So technetium is unique to any other element because it has a unique number of protons, but it can have different forms. When I say form, it means it has the same number of protons because it's still technetium, but it can have different number of neutrons. Why do we care? Well, some isotopes, because they have a different proton to neutron ratio, are radioactive, so we care about what isotope we're dealing with. So again, it's about different number of neutrons, different mass number, same number of protons. Let's get that down in the answer booklet. I say isotopes have the same number of protons but a different number of neutrons. I could be more specific and say atoms of technetium have 43 protons, because I would go to the periodic table and see its atomic number is 43, but I can have a different number of neutrons. There's many ways to say this, but they told you in terms of protons and neutrons. So if you didn't answer them, you'd get this wrong. So again, got to get your isotope understanding down. On to number 53. On to number 53. Show a numerical setup for calculating the volume of this sample of gas at 298 and 1 atmosphere. So I had a little blurb up here. And I know I always go to the question, but sometimes you have to go back. But what I will say about this question is they want just a setup. So therefore, this is going to be some kind of calculation. So I need a formula. But notice they're looking for calculating the volume. Notice I'm at a temperature and there's a pressure given to you. So my friends in chemistry, that this is a gas law problem. If I go back to the blurb, sometimes I have to, I can say I have a gas that's originally is in a rigid cylinder with a movable piston, and it has a volume, an original volume of 0.25 liters, and it's at STP. So we have a volume of a gas. Remember, a liter is a space, it's a volume, and it's at a condition of standard temperature and pressure. Now, if you forget what STP is, we can go to table A, and they'll tell you those values, but STP is just a word that describes numbers. So we have a volume initially at standard temperature and at standard pressure. And 53 is asking, what would be the new volume if I change that temperature to 298 Kelvin and I change that pressure to 1 atmosphere? So this has got to ring some bells that this is a gas law problem. and I need a gas law equation to solve this. Okay, even though we're not solving, we're just going to plug the numbers in. So what becomes tricky for a couple of students is, hey, what is the values for STP? So many students say I can't do this because I don't have any numbers. So I understand that we need to know what the values are for standard temperature and pressure, and we need a formula. So that's where we're going to go to our tables. We're going to go to table A for STP, and then to table T for the actual formula for the gas laws if you don't remember. So let's go there. Here is table T in all of its glory, and we are looking for, of course, we're looking for our combined gas laws, right? So zoom up close and personal here, we see that it's PV over T equals PV over T. And I always say this is the current condition, right? And this is the future. I don't know if we talk like that in the future. So what are they giving us initially? And what is the new conditions? All right, so the problem is they gave us a volume, okay, but they said STP conditions. So we need to know what the pressure is at STP and the temperature. So we're going to go to table A to get those values. All right, let's do that. And so there it is. Standard pressure is either in kilopascals, 101.3, or in atmospheres, and 1 atmosphere is standard pressure, or standard temperature, of course. It has to be in kelvins if you're going to use it in a gas law formula, but it represents 0 degrees Celsius as well. So those are the values. Make sure you use the pressure unit, okay, that matches the unit that's given in the problem, so they would cancel. All right. So in any case, let's get back to the problem. The information is right at your fingertips in your reference tables. You have 3 hours in this test. Please go through. And maybe if you didn't recognize it was an acid-base problem, looking at table T and table A, you can warm up the thoughts, okay, about what this problem was about. Now we're going to have to answer this in our answer booklet, but just remembering what we have here, we have 0.25 liters, okay? So we have 0.25 liters at STP. So we're going to plug in the values of P, pressure and volume, what STP represents from table A, and then we're going to change that what the new volume we're going to solve, or at least plug in what the new volume will be for 298 and 1 atmosphere. Okay, so let's get to the booklet and put that in. So you can see that we have our STP conditions here, and so this value here is STP, this value here is STP. We had our original volume given to us, that's the current scenario. And then they said that what if the temperature changes? And of course they gave us a pressure for the new, but notice it's the same as the original pressure, that's standard temperature. And you solve for the new volume. Okay, so this is the setup. It's all they wanted. They didn't want you to answer. Now, if you did answer the question by cross multiplying, that wouldn't be wrong, as long as you showed the work, right? Because that's what they're looking for. They're looking for the setup. By the way, you don't really need the units, but it's really helpful to put the units on, and they have to be the same. So it's important that because this was in atmospheres, this number here had to be in atmospheres, right? So if you use 101.3 kilopascal, which is an equivalent, okay, that would be wrong. You needed a 1 atmosphere here, because that would cancel. If you were to solve for V and set this up, it would wind up canceling, and 101.3 wouldn't. So you got to make sure that a little tricky there, little trick there, not a trick, but something to be aware of. The units have to be the same. Okay, but if you notice something, you could have eliminated the pressure altogether because it's staying constant. So you didn't even have to put in those values. So it could have just been the 0.25 over 273 and V over 298. Okay, either way you want to write it, that's the setup. Okay, and that's a point, and not very typically very difficult, but you have to recognize this to be a gas law problem. There's pressure, there's temperature, there's a change. And table T is your friend here in terms of these formulas. And of course, STP, they represent values. Okay, so on to number 54. Number 54, state a change in pressure that will cause the gas in the cylinder to behave more like an ideal gas. Okay, so what is an ideal gas? Well, an ideal gas is a gas that doesn't exist. There are conditions we call ideal, which means it would, if it acts under these set of conditions, it would follow our gas laws perfectly. So what are these conditions? Well, we need gases to be independent particles. We need them to fly in the open space or the volume of space they're flying in and move independently of each other. So the biggest factor of an ideal gas to remember is that ideally they have no attractive forces. I have this thing that I describe this with my students. An ideal gas is an ideal student. Ideal student comes to class early, moves fast, gets there by going in straight lines because it's not really involved in all the drama and all the things. It has no attractions for the people around them. It's just there for school. Obviously, that's an ideal scenario. It doesn't exist. Same thing for an ideal gas. But ideally, if they're perfect, like the perfect student, they will have no attractive forces between them, because real students really like other people and move in curved pathways toward their friends and not always focused on school and teaching, right? So no attractive forces, okay, or intermolecular forces, they're not bonds, existing. So how can I deal with pressure and make a gas that has some attractive force have less? Well, I think of two things. So an ideal gas, all right, I can teach this the way that I'd love to, and then I'll give you the easiest way to do it. So the ideal gas, okay, is going to have gas particles that are farther away moving independently in straight lines. A real gas, like a real student, is going to be closer to the other gas particles, not independent, because there's going to be some attractions in between. Okay, so how do I make a real gas be more like an ideal gas in terms of pressure? Well, I want them to separate. So I want to decrease the pressure on them so they can be farther away. So the answer is decrease the pressure. Now, if you can't understand the things that I'm explaining here, one easy way to remember this is the word plight. Okay, so P-L-I-G-H-T. Okay, and for an ideal gas, the pressure has to be low and the temperature has to be high. They're not asking for an ideal gas, and they're not asking for temperature, they're asking for what the pressure is. So pressure is low for an ideal gas. So another way to remember that. All right, so lower the pressure. Let's put that in the book. We would lower the pressure, which means the molecules will exist farther away and have less chance to attract and be more as ideal independent gas particles. Okay, on to 55. 55 has a huge blurb, including a procedure with data. And again, we could sit and spend 10 minutes trying to understand it, or we can go directly to the problem and see if we have to go back. Again, a lot of these don't require you to completely understand what's happening, and some do, and you have to go back. But I think the best way is go right to the question. Don't be intimidated here by the setup. If you don't recognize it, if you didn't do it, let's figure out what the question is first so that we can kind of get a sense of thinking of what we have to do and what we may need to solve for it. So 55, state the direction of heat flow. Oh my gosh, state the direction of heat flow. So heat flows from, okay, hot to cold, okay, between the candle flame and the beaker. So they're screaming to you, tell me how heat flows from the candle flame and the beaker while the candle is lit. I don't think I need to understand, but something burning is going to be much, much warmer and hotter than a beaker of water that boils at 100. So I hope you can probably understand that the energy is going to flow, okay, from the candle, okay, to the beaker and into the air, right? The candle is burning exothermically, which means the surroundings increase in temperature. Right? Anything that's exothermic that gives off heat, the temperature increases. So how does the water increase? Well, energy is flowing from the candle to the beaker. I just don't know how else to explain that. Okay, hot to cold. It's a really entropy too. So let's get that in our answer booklet. I just wrote from the candle to the beaker, and I said to myself, well, I probably should say candle flame, but they'd accept either way. So the energy is going from the candle or the candle flame to the beaker. Okay, they asked specifically what the flow is, and of course they kind of set this up for you in the answer booklet to help you direct it to the two different things. Okay, so from the place that gives off the energy to the place that accepts, from hot to cold, it's how the universe works. It's really an example of entropy. On to 56. So number 56, show a numerical setup for calculating the amount of heat in joules absorbed by the water in the beaker as a result of the burning candle. So it's about heat, it's about energy. And guess what? You're calculating, you need a formula. So my gosh, a place to look for formulas if you need to calculate something is table T. Now, notice they said they want you to show a numerical setup, so you're not looking to do what? Solve this. You're looking to just plug it in. So we need a formula, and then we're going to have to look into this blurb of information here to solve for it. Let's go find that formula. Bottom of table T, I have 3 formulas here that represent Q. Q is heat. Now, only one has a change in temperature. So we can guess that if we have a candle flame underwater, that's not under a phase change. It's not boiling, it's not melting, it's not condensing. We should know phase changes are physical. And 2, the kinetic or temperature doesn't change. So we don't have a phase change. These formulas here are used for when you don't have a temperature change. So we're not going to use these. We're going to use Q equals MC change in T. And they tell you the M is the mass, and the C is the specific heat of water, and there's a change in temperature. If you've got a candle underwater, you know the water is going to go up in temperature. You may say, well, what's the specific heat capacity? What value is that? And that would be table B. And since this is about water, these are physical constants of water, we have our specific heat 4.18. I'm sure you used that plenty of times in the examples that you learned in your class. Again, this review of seeing questions is important for you guys to help you warm you up to review the things you've already learned. So that C value is that value. That really measures how much energy is needed to change 1 gram of it 1 degree Celsius, okay? And water has a high specific heat. So it's back to the problem. Loaded with our new formula, what we have is Q is equal to MC change in T. I'm saying it big, bad, and bold here because you should have it down. So we're going to measure energy change, and we need to know the mass. And people get confused. What mass do I use if there's a block? It's always, this equation is always for the same team. It's always of the same substance. So it's always about the water mostly, but it could be of a metal block. But then we would need what? The change in temperature of that other object and its specific heat. So it's always of the same substance. So the mass of the water is 120. The specific heat, okay, is 4.18. We got that from table B. Now we need a change in temperature. Well, it was initially at 23, and as we added the candle, the heat traveled to the, of course, beaker, and it went up. So we're going to have to subtract these 2 values to get our change. Okay, so you can use a calculator. Don't be foolish like me and do it longhand. But since I've lived before the calculator age, just joking, okay, I'm going to give it a try. So I get 63 degrees Celsius is my temperature change, and that is what I put into the formula. 4 degrees Celsius. That is great, but I need to put it in my answer booklet. Here it is. I'm just plugging in the numbers. They just wanted the setup. Yes, it equals Q, but you don't have to write that. You don't even need the equal sign. I just need to show that these numbers are multiplied together. That's it. If you were to show that in this, you could have written 86, 0.0 or 86 minus the 23. You could have put that value there too. And some people converted to Kelvin, which is crazy, and then subtracted. We should have the Kelvin and a Celsius are the same size. So that when you subtract in Kelvin or subtract in Celsius, it's the same amount. Kelvin just takes the Celsius scale and starts at 273 degrees sooner. But yeah, it's just that simple. All we need, party people, is just this. And of course, you don't need the units. You could round to 4.2 right here, you know, and again, that's the basics of what they want. Very, very straightforward, and we'll take it where we can. But again, it's the identification that you're measuring energy. I'm sure you've done some lab that you did that you can connect with. Oh, yeah. But just don't forget, this is always from the same team, because they love to give you questions where like there's a metal block or something else, and they'll give you two different masses, and people don't know what mass to put. Remember, this is MC, change in T, but it's always of the same substance. So this is the mass of the water, right? This is the specific heat of the water. This is the temperature change of the water. Okay, very important. On to number 57. Number 57, state how the molecular motion of water molecules in the beaker changes as temperature increases. Well, you need to know temperature, my friends, is proportionate. It's not the same as, but it's proportionate to kinetic energy. When I say proportionate, it means as temperature increases for a substance, that means its kinetic energy increases. So as temperature increases, kinetic energy, which is the energy of motion, increases. And so molecular motion is kinetic energy. So state how the molecular motion of the water changes as temperature increases. My friends, it increases. Temperature, you should know, is proportionate to the average kinetic energy. This is going to be presented to you in some place in your question. I've seen multiple choice questions where they say, which of the following has the highest average kinetic energy? You'd pick the higher temperature no matter what size, because it's an average. What's the highest average? It's indicative, or it's independent of the size of the mass. So temperature is the average kinetic energy. And you have to know that kinetic energy is motion energy, which is molecular motion. So nowhere, it's all about the fact that if the temperature increases, the molecules are moving more in that sample. If the temperature decreases, they have less energy to move, and they move less. So onto the booklet. The molecular motion increases. You can say the average kinetic energy increases. You could say the water molecules collide more often and hit harder as temperature increases. That's an important one. You should know that as things move faster, each collision has more energy, and there's more collisions. That does come up, but that's not what they're looking for exactly here. They're looking for the idea that, hey, they're just moving faster. And you could just say that molecules of water are moving faster. All right. So there's many ways to say the same thing. But remember, the key here was that temperature is proportionate to kinetic energy or motion energy. All right. And so temperature went up, so does the motion energy. On to number 58. Number 58. Compare the rate of the forward reaction to the rate of the reverse reaction when the system is at equilibrium. Oh my gosh, another freebie. Okay, if you're at equilibrium, reason why we have a double arrow here is because the forward reaction goes as fast as the reverse. Again, so the rate of the forward equals the rate of the reversed at equilibrium. These are some things you just have to know, and that's what they're asking. I could care less about the blurb. Okay, so it's got nothing to do with that equation other than it's an example of a reaction equilibrium, which means the forward rate or speed is as fast as the reverse rate. That's what equilibrium is. The best example I can teach you is if I have a line with 3 people on one side of the room, and I have a line with 11 people on the other side of the room, and I ask the people on each line to switch places 1 person at a time per minute, okay, then what we're going to get is 1 person is going to go to this line as fast as 1 person goes to this line. So 1 person's going to switch lines every minute. And so the rate of going to each line is the same, so we're at equilibrium, but something else pops up here. Even though they're not asking about it, I want you to understand the entire concept behind the question. The number of people stay the same. There's always going to be 11 people on this line, even though the people might change. That's why they call it dynamic. Dynamic is changing. And there'll always be 3 people on this line. because they're changing positions equally, or the rate of changing is the same. So the rate of the forward equals the rate of reverse, and because of that, the amount of them stay constant. Now, the word constant's not part of this question, but it will be in others. So be aware that equilibrium, rate of the forward, equals the rate of the reverse. Always, I've seen this in multiple choice questions. It's the same kind of question. Because of it, the amount of reactants and products stay constant. Onto the booklet. It said here the rate of the forward reaction equals the rate of the reverse reaction equals is the key thing here. I could have just said equals. I mean, they give you all this space here. But don't feel like oh my God, they're giving you all these lines. These answers have to be long and winded. No, don't do that. Get to the point and get out. So there you go. On to number 59. Number 59. State how the equilibrium shifts. So this is the Chatelier's problem, where we want to shift out of equilibrium when the pressure of the system is increased at constant temperature. Okay, so we get a reaction at equilibrium. The forward reaction goes as fast as the reverse. When we say a shift, what we're going to say is one of the directions, either the forward or the reverse, now is going to get faster than the other. Remember, at equilibrium, the speed of the forward or the rate of the forward equals the rate of the reverse. So they're both going at the same speed, and the amount of the reactants and products stay constant. But if I can cause a shift, which direction? The shift represents one of the directions going now faster, which means you're going to lose, okay, the things you're shifting away from and increase the ones you're shifting toward. Okay, so there's a stress and then there's a response. So the way that I teach this is that if you give yourself a little chart, we have a stress and a response. The stress is that the pressure is increased. Now the reaction wants to shift to regain its balance. Things in nature always work toward equilibrium. Equilibrium is a low energy state. Okay, so therefore the pressure has gone to what? We're going to push it out of equilibrium, and then it's going to want to lower the pressure to regain its balance. So the response, okay, the response is always going to be in the reverse of the stress. Stress is what people do. The response is what the reaction does. And the reaction is going to shift either left or right, go faster toward the left or go faster to the right to regain the balance. If you have no idea how to do this, you're either going to say shift left or shift right. It's a 50-50. Anytime the pressure is a stress, you count moles of gas. Okay, so in my problem here, on the reactant side, I can see there is 2 moles of gas. On the product side, I see there's 1 mole of gas. So if the reaction wants to lower the pressure, doesn't it make sense it's going to shift to the side with less moles of gas? Of course it does, because particles of gas collide. They create the pressure. So this means that this reaction is going to respond by going faster in the forward direction to lower the total number of gas particles and then subsequently the pressure. So we would say shift to the right. All right, to the booklet. It shifts to the right, okay, or it shifts to the side with a few moles of gas, or it's going to favor the forward. Favoring the forward means the forward's now going faster. Okay, shifting to the right means that we are now going faster in the forward direction. Okay, all right, so a little Chatelier's problem there. On to number 60. Okay, number 60. Compare the entropy of a sample of dinitrogen tetraoxide gas at 25 and 1 atmosphere to the entropy of the same compound, or I should say, sorry, the same compound but at a liquid at 15 degrees Celsius. So what we're really doing with all these words is we're comparing the entropy of a gas to the entropy of a liquid. Now, of course, what is entropy? Entropy is the measure of randomness. It really is a measure of how energy disperses outward, but you can think of it as the spreading out of energy. Things in nature spread out. When they're together, there's more potential in terms of, I'll just say that things spread out naturally in nature. Leaves on a tree break down into smaller and smaller pieces. It's how the universe works. Our universe is expanding. So when you think of entropy, think of the spreading out of energy. And the way that particles can do that is when they become individual free particles, they can move independently. Solids have lower entropy because solids exist in a three-dimensional structure called a crystal lattice. Here's one example. Sometimes you have to draw it. It's a regular repeating geometric structure. And the next what? Particle or atom has to be in the next spot of the crystal. And because these guys can't move independently, all they can do is wiggle in their fixed positions. They don't have a lot of randomness. There's a lot of order here, a lot of structure. Okay, now when they become a liquid, they're free of the crystalline structure, but they still have a lot of attractive forces. Liquids have to basically stay in their container. And then, of course, when they become a gas, they have the greatest molecular motion or degrees of freedom. And therefore, they spread out a lot more than a liquid can or a solid can. And their ability to spread outward and have their energy dispersed, okay, or they have a lot more random motion is going to occur for a gas. So the entropy for a gas, okay, is going to be greater than a liquid. And interesting enough, they give you different temperatures. If this was still a liquid and the liquid was increased to 25 from 15, the entropy would also increase. If you add energy to a system, they're going to move more. And if they move more, they're going to spread out more. We know that the density of a liquid decreases as it gets warmer, okay? Right? And the density of a gas decreases as it gets warmer. That's how hot air balloons work, right? So that's the same idea. The ability to spread out, be independent, be more random is how the universe wants to work. Energy that's, stored in a small area wants to be free, okay? And we know that gases have greater molecular motion. So in any case, you would say that the gas, of course, has greater randomness than the liquid. The entropy is greater in the gas, and certainly you can phrase this so many different ways. The entropy of the dinitrogen tetraoxide in the gaseous phase is higher than the liquid dinitrogen tetraoxide. If you want to work, use all those words, but you don't have to. The entropy at 15 degrees Celsius, you can just talk about temperature, right? Forget about the phase, is less than that of 25. As things get colder, they move less. They're less degrees of freedom. They don't spread out as much. Okay, so many ways to say that, but the gas, of course, spreads out. It's more random than the liquid. On to number 61. Number 61. Going right to the question. State the change in oxidation state of copper in this reaction. Okay, party people, we've got to know that the copper is a standalone element. If it's standing alone or just bonded to itself, you've got to know it's an atom, right? And I say atom, you should say neutral. Atom, come on, say neutral. Atom, neutral. Atoms are neutral because their protons equal their electrons. So standalones are zero. They have no charge because their protons equal the electrons. All elements or atoms in the periodic table are written as atoms. So the atomic number is equal to the electron number. Now, when it bonds to something, it changes. Okay, so what is copper? Okay, so we know it's going from copper 0, but what is it changing to? Now, once it's bonded to something, it can't be a 0 because now it went under a redox reaction. It's going to lose electrons. Standalone metals can only oxidize, but in any case, it's not really what this question is about. What the question is about is what is the charge on the copper here? So this is an ionic compound. It has to equal 0, but the components have charges. So what's the charge of nitrate? Notice there's two of them. If you don't know it's -1, okay, there's a place to look. Let's look. So table E I call what the heck is that table? These are the clusters of normally mostly nonmetals that bond covalently and have a charge, and therefore they can make ionic compounds. That's why some questions will see which compounds have both ionic and covalent. You look for a polyatomic ion. But in this question, we're here because we want to know what the charge of the nitrate ion is. The nitrate ion is negative or -1. So the nitrate ion, not the nitrate ion. Nitrate ion, not the nitrite ion. I can do this. Okay, so any case, this ion right here, the nitrate ion we're after, is -1. Okay, and that's really important because there was two of them bonded to copper. So that means the collective charge of all the nitrates is -2. Since there's one copper, copper is +2. But let's look back on that if you don't remember. So because each nitrate's -1 and there's two of them, that means the overall charge due to all the nitrates is -2. Remember, the whole thing has to equal 0. Ionic compounds equal 0. Since there's only one copper, the copper must be +2. So what are they looking for? They're looking for the change in oxidation state. So I would say it goes from 0 to +2. Okay, let's get to the booklet. So from 0 to +2, and notice the booklet really helps you define how to answer it because we weren't sure what to say there. You can also say from copper to copper +2. You could do that as well. Okay, or from 0, you can write the words out if you want. Okay, so again, 0 to +2, pretty straightforward. Okay, number 62. Number 62. Based on table J, they're telling you to go to table J. State why copper reacts spontaneously with silver plus. I'm having a tough time speaking this afternoon. So why does copper react with Ag plus? Now, it's important you understand what this is because it can get a bit confusing even though I have trouble speaking today. So copper in a redox reaction, because this is what this is, oxidation numbers are changing, can react with Ag plus. Now, think with me for a second what this is about. Standalone metals can only oxidize. So when you see a reaction like this, okay, any metal hanging out by itself is oxidizing only. Copper cannot gain electrons and become negatively charged. Copper +2 can. That's different. But all metals written by themselves, like magnesium, gold, silver, they're 0 and they only become positive by losing their negatives or oxidizing. So I know that the copper must oxidize if this is going to work. The one who has a charge, in this case the silver plus, has got to reduce. So the way that they wrote this reaction, they said the word spontaneous. Now what that means is that it's going to react without any input of energy. And it only works if the one who is oxidizing is strong enough to force its electrons on the one who's reducing. Okay, so we have to recognize that Ag plus can only get reduced. And how do I know that? Because Ag plus, okay, is not a standalone metal. It's not hanging out by itself. It can gain an electron, which it will in this process if it works. We have to find out if it does, and it will become Ag0. It's going to gain 1 electron. Okay, copper, if it gives 1 electron up, is going to become copper +1. So this would be the net ion equation if 1 electron was being passed around and if it was spontaneous, if this can work. You've got to see that. So the one losing has to be the one who is oxidizing. But again, to pick out who is oxidizing, find your standalone metal in the reactant side. Now, to know if this works, we go to table J, and there's a list of metals. The metals who are best at oxidizing are on top. So comparing copper with silver, you're just seeing if copper is higher than silver in table J. And if it is, that means copper can oxidize better than silver, so it can push its electrons onto the silver plus, and this will work without an input of energy. Okay, so let's go to table J. Well, there it is, and there's our list, okay, of metals. The most active are the ones that react the best. Metals that stand alone are active by losing electrons. Metals lose electrons. Guess what nonmetals do? They gain. So the list over here is who's best at gaining. Gur means reduction. So this is a list of who oxidizes the best. So if copper is going to oxidize without an input of energy, that's what spontaneous means, it's got to be higher than silver. And so is it higher than silver? Yes, it is. So when you put copper next to silver ions, the one highest, if it's higher, will spontaneously react with the metal who's going to be an ion that reduces. The higher one always oxidizes. So since copper is higher than silver, it will oxidize spontaneously. So based on table J, why does copper react spontaneously? It's just higher on table J than silver. That's all you need to do here. I said copper is located higher in table J than silver. Okay? You could say silver is less active than copper. Copper is more active. Okay? That's all there is to it. On to number 63. Number 63. Write a balanced half reaction equation to represent the reduction of the silver ion. So Leo the lion says Gur, so gaining electrons is reduction. You can also do oil rig, right? Oxidation is losing, and then reduction is gaining. I don't care what you do, but since we're talking about reduction, we know that we're going to be gaining electrons, and we got the silver ions. And they told us what the silver ions are. They're Ag, well, they're Ag+, okay? They're right there. And they tell you that in this equation too. Nitrate's -1, so silver is +1. So what's the half reaction? We're going to start with our silver plus. That's the reactant. We're not changing sides. So the silver plus comes from that side, right? That's +1. That's +1 because we learned that in table E, nitrates are -1. So we really have Ag+ there. Now, it's going to become what? Well, it's going to become a silver, a standalone silver. Okay, so I write Ag and I put a 0 here. How does that happen? How does a +1 become a 0? Remember, both sides have to have the same charge. Well, again, they said reduction, gaining electrons, or reduction is gaining. I don't care. I need an electron right here. Okay, +1 E negative. And the way that works is both sides of a half reaction have to have the same charge. By putting the 1 electron there, +1 is 0 is a difference of 1. This is a 0, and this is already a 0. That's perfect. If you put the electron on this side, that'd be incorrect. A -1 and a 0 is -1. This side's +1. So again, where you put the electron is important, but reduction is a form. Okay, reduction is a form of gaining electrons. Okay, and so you should know gaining something like gaining energy, it's like endothermic electrons are on the reactant side. Okay, so that's what we put in our answer book. 53, there's my ion, and there's me gaining an electron here and making a silver. Now, they could accept a couple of different things. If you notice, there was actually 2 silver ions in their reaction, so you could put 2 electrons here, and this would make a 2 here across the board because of conservation and mass. So that could be accepted too. I say keep it simple. For every 1 silver plus and 1 electron you make, 1 silver 0. Okay, so bottom line is we're gaining electrons. Electrons are on the reactant side. Both sides of the half reaction equals 0. Okay, so make sure you've got that down. It's a great little check here, but that's a reduction, a correctly balanced reduction reaction. The charge on one side is the same as the charge in the other, and there is 1 silver on one side, and there's still 1 silver. So mass and charge, okay, are both still conserved there. So on to 64. Number 64. So again, we have this blurb, and I'm going to go right to the question. Write the name of the laboratory procedure used in this activity. Guess what? Gotta go read the blurb in this case. So during this laboratory activity, we have a certain amount of acid is exactly neutralized by a certain amount of base. This should scream to you a certain procedure. Every single, I would say, Regents students should have done a procedure where you took a burette, which is an emptying device, and normally you'd fill it with the base, but it could be done the other way. And you would add it to an acid like HCl, and you would figure out the concentration, or you would figure out something about each other by dropping base onto acid until all of the acid has been neutralized. And we use a chemical indicator to help us get an approximate spot where we stop adding the base to the acid. And using a certain formula, we can actually solve for the molarity or the amount of acid or base needed to neutralize. This is called a titration, okay? And we use acid-base titrations in Regents Chemistry, but you can also do gravimetric titrations or redox, volumetric redox titrations, where you're matching the moles of one compound with the moles of another compound it reacts with. In the case of acid and base, the key is neutralized. You hear the word neutralized, and you see, I always say if you see three, variables, in this case, the milliliters of the acid, the milliliters and molarity of the base, this screams to you acid-base titration. So the word titration just really means that you're using one chemical's information to answer another in a laboratory procedure. So knowing how much, sodium hydroxide I'm adding, I can figure out exactly how much acid I have, because generally speaking, the acid, in this case the H plus or H3O plus, equals the equals the hydroxide for the base when it's neutralized. And the word neutralized means we take away the danger of each of these ions. In high concentration, H plus is very dangerous because it can break down, react with metals, it could break down flesh. And the same thing with hydroxides. They're just as dangerous in high concentrations. High concentrations of hydroxides can break down organic material and metals as well. And they're dangerous at high pHs. And of course, having a lot of H pluses or H3O pluses are also dangerous at very low pHs. But if you add a base, the right amount or the exact amount of hydroxides to this dangerous H plus, you can neutralize both, because they're going to become just water, and water isn't dangerous. So that's what neutralization is. So any case, we're talking about a titration, an acid-base titration. Titration is the word, and I've seen this answer in this type of question given in a multiple choice section. So going over the multiple choice, you're not inhibiting or hurting your studying for the part 2. It's the same type of questions, just kind of hidden. They accept a volumetric analysis too, but they do not accept neutralization, because I believe that's just kind of repeating the word neutralized. So 64 is titration. On to 65. So number 65, show the numerical setup. Another question where they just want you to put the numbers in. Therefore, you need a formula for calculating the molarity of the HCl solution. Very classic Regents question. It's on every Regents, whether it's on the multiple choice section or in the free response, and here we are. So we want to calculate the molarity. We want the concentration. Molarity is big M. We want to know the molarity, and oftentimes that's the reason why we do a titration. You can see where I've highlighted, those are the values given. There's 3 of them, and there's a big M involved. And we learned from 64 that this is a titration experiment where we're neutralizing. The key words are neutralized, acid and base. You see big M. There's 3 variables. So we need an equation with 4 things. So let's go to table T to remind ourselves in this 3-hour test where I can look if I forget to jog my memory. Here we are in table T, and looky here, we've got a titration formula. If you don't get that, look at this, the molarity of the H plus. There's the word acid, there's the base, all these keys to help you remember that this is the formula we use to figure out the other chemical, in this case the acid or base, given information about the acid or base given. So MV of the acid equals MV of the base is what we use here. This happens every test. See more questions. You'll see more of these questions. You'll see more test questions, or see more total tests and do them. You'll see this particular question popping up at least once every test. So let's get these values in and get this answer done. I need the titration formula for this titration procedure, acid and base. Let's plug in our values now. Okay, so they gave me 15 milliliters of hydrochloric acid, so that's my 15 milliliters, that's my volume. We don't know its concentration. They're calculating the molarity of the acid, so that's my unknown. If you want to keep that, you want to use an X, that's fine. And then what's the molarity of the base? Hey, they gave us 0.11, and they gave us 18.2 milliliters. My friends in chemistry, that's all there is to it. You're just going to plug that in. And in fact, they're not looking for an answer. They just want a setup. You could solve for it. It wouldn't be wrong. Let's put it into the booklet of fun. There it is. M of A, V of A equals M of B, V of B. MV of the acid equals MV of the base. We're just plugging into what they just gave us. Okay, understanding what a molarity is and what a volume is, and we're solving for the unknown, except we're not solving, we're just plugging in because they just want the setup. So what I have here is perfect. Okay, certainly you could start solving for this and put this under 15 if you wanted to, but again, the way you just plugged it in and left the unknown as it is perfectly fine. No reason to get that wrong. These questions should be getting similar. And if it's the first time you've seen this, you need to do more tests, okay, to see this titration volumetric problem. Common, one of the most common math questions on the Regents. On to number 66. Number 66. Identify the 3 endangered elements listed in the passage that are classified as metals. So I like to go right to the question, and I did, but it looks like I have to go back. So I looked for 3 endangered. So I got to go back to the reading into what I call the blurb. Okay? So they say several elements are endangered because there's a risk these elements become unavailable for commercial uses in the next 100 years. And that would be helium, zinc, and gallium, indium, and tellurium. All right, so that's the little blurb. So identify 3 endangered elements. So you make sure you definitely have your 3 there. Listed in the passage are classified as metals. So again, from the list they give you, can you figure out who your metals are? So we should know our metals are to the left of the staircase. The staircase is built by the metalloids, have properties of both metals and nonmetals. So if I look at these, I know helium is up to the right. That's a nonmetal. I know gallium, well, indium, tellurium. So you may see yourself, oh my gosh, I don't know where these are. So we're going to have to go to the periodic table to see where they are. If you forgot helium was up to the right and a noble gas, okay. But zinc, gallium, indium, tellurium. So 3 of them are metals, or at least there's at least 3 there, hopefully. Okay, so let's go to the periodic table. These are the elements that were given to us: helium, tellurium, indium, gallium, and zinc. Okay, so where are the metals versus nonmetals? Well, you should know, my friends in chemistry, that we have this staircase here, okay, and it basically breaks down the difference between the small atoms that love to attract electrons to the big atoms that love to lose them, the metals versus the nonmetals. Now, all of these elements on the staircase are metalloids. Okay, so boron, silicon, arsenic, tellurium, and we can include astatine if we'd like. It also includes germanium and antimony. We should know those are the ones. So you can see that tellurium is right on the staircase, so that is of course a metalloid. We should know that all the elements above and to the right, okay, of the staircase are nonmetals. There are the smallest atoms, And the electron, they have the greatest number of protons in their energy levels for the most part, so they love to attract electrons. Probably could write that smaller. That's their nonmetals. And over here is the vast land of the. By the way, the one Waldo. If you ever looked at Where's Waldo, where is the picture that's different? Hydrogen is a nonmetal, and it's put over here because of one electron. So be aware of that. So in any case, all the rest of these elements that are to the left of the staircase or below it are metals. So zinc, gallium, and indium are your metals. Now something else we can look at very, very close, if we get up close and personal with these guys, okay, we can see that these all become positively charged. They never ever become negative. So metals are unique because they only become positively charged, right? So that's important that you get that. So only, oh, that's not what I wanted to do there. Essentially, these guys are metals because they're also only become positive ions. They like to lose electrons. It's really, really big. So zinc, gallium, indium, to the left of the staircase, okay, are your metals. Or they're the only ones that only become positive ions, which means they only lose. Leo, losing electrons, is oxidation, okay, as well. Those are really, really important concepts. So back to the question. So as we said, it's going to be zinc, it's going to be gallium, and it's going to be indium. Okay, we got to get that into the test booklet. Let's go. Right, gallium, indium, and zinc. You certainly could have written their chemical symbols. So Ga, Zn for zinc, and In. And if you didn't know indium or gallium were Ga and In, you certainly could go to table S, right? Table S will give you the names using the symbol. As long, it also gives you all that other information that table S, people forget all the time, most underutilized table. So I didn't cover that part. Any case, on to number 77. On to number 67. Number 67, explain in terms of electrons. Party people, they're telling you how to answer this question. So please do so in terms of electrons. All right, so why gallium and indium have similar chemical properties. So why do they have similar chemical properties? They do so because they bond similarly. Why do they bond? Their outermost electrons are similar. Their valence electrons are the same if you're in the same column. So that's something they love to ask on these tests over and over and over. So similar chemical properties because they have the same valence electrons. If you don't know that, let's go back to the periodic table. She is in all of their glory. The two atoms are in the same column. Why are they in the same column? Because they're related. They're in the same family. We don't have a name for these that we have to know, but you can see that the outermost electrons, the most unstable electrons, is 3. Therefore, they love to lose those outermost, and therefore they all become +3. Notice aluminum. I know it's hard to see there because I had it erased, but aluminum likes to become +3. Okay, and boron, don't be one, notice it likes to become +3. So party people, the reason these guys lose 3 electrons is because they all have 3 valence electrons. They all will bond very similar. Therefore, they have the same chemical properties. You've got to know that in the same group, same valence, same chemical properties. The answer is they have the same valence electrons. Okay, and I probably should say the same number to cover myself. So the same number of valence electrons. Okay, and I was going to say that with an exclamation point, same number of valence electrons. Same number of outermost electrons, or they all have 3 valence electrons. You could say it so many different ways, but that's a common theme in this course. All right, on to number 68. Number 68. Compare the density of a sample of helium at STP with the density of a sample of tellurium. So my friends, in chemistry, we're comparing the density of the helium and tellurium, 2 out of the 5 endangered elements. There's nothing in the what? There's nothing in the blurb here that talks about density, but as I keep saying, the most underutilized table that gives us so many things that people forget for this test is table S. Yes, I'm pulling out the exclamation point. All right, so let's go there. Just look up the density of helium and compare it to tellurium. Now, my gosh, we could do that, all right, but you probably know helium is a noble gas. Tellurium, as we have been using in the other problems, based upon where it is on the periodic table, it's a metal. Almost all metals are solids, and helium is a noble gas. It is definitely a gas. You fill balloons with it, play with them in the park, and watch them deflate. And some people forget it. Any case, so metals are that usually exist in the solid phase will have a greater density. So that's just some common ideas there. But if you're unsure, because there is one metal that is a liquid, but there are no metals at STP that are gases. But if you're still unsure, you can go to table S and look these up. All right, and I don't think I need to hold your hand there. Okay, so mercury is another metal, Hg, that's a liquid. Okay, and therefore mercury would still be more dense than the gas. So all gases are metals or solids, except for one, that's mercury. But you know what? I'm going to take you there anyway, because you should know how to identify solids, liquids, and gases from table S. Any case. So let's go there. It's going to be a lot of fun, I promise. So back here at table S land, which again, the most underutilized table. Okay, all these things are given to you. So we look at helium, and it's got a very small density. Why? Well, because it's a what? Gas. Gases are farther apart from each other. They have kinetic energy. It should be very understandable that gases, compared to liquids and solids, are the most diffuse and less dense. Okay, now if we stroll through this to tellurium, atomic number 52, all right, I'm going to see, oh, it's above iodine. I guess I was using this somewhere. So if I go to 52, I see that the density is much higher. So it's really, really unfortunate to not be able to get this kind of question right. So tellurium, again, its value is 6.2 grams. All right, so much, much higher than what we had there. But how do I know? How do I know that tellurium, okay, is a gas or a solid or a liquid? Okay, for those that didn't watch earlier, very simple. Okay, look at tellurium, look at its melting point. Okay, its melting point is 723. What does that mean? Well, we always compare it to STP, and standard temperature is 273. So what does that mean? It means that after 273 or above 273, it melts. So at 273, it has not melted yet. So it's a solid. And its boiling point, well, gosh darn it, it certainly hasn't boiled yet, because 273 is so much colder than 1261 kelvins. All right, and if we check out, if we go up to helium, we can see that its boiling point is 20 kelvins, which means, heck, that's way before you hit 273, so it's boiled already, it's a gas. So in any case, all those things lead to the answer we have to write in our booklet, which is that tellurium, a solid, has larger density than the gas, or as what table S is showing us. Amazingly, tellurium is more dense than helium. They didn't ask for why. Okay, so there you go. On to number 69. 69, explain in terms of what? And they're telling us how to answer this? Explain in terms of electron shells. So guess what? That better be in my answer. Why the atomic radius of an atom of indium, okay, is greater than the radius of gallium. Okay, so why is indium larger than gallium when both atoms are in their ground state? So if we're not sure again where indium is in relation to gallium, because that's what this question is about. All right, so where is indium in relation to gallium on the reference table? Let's go to the periodic table and find out. Indium and gallium are in the same column as we've seen in other questions. And if they are, that means they're in different rows, which means they're filling different number of shells. Now, if you look carefully, gallium is in the 4th row, right? So the first row is here with helium. Here's the second row. 3rd row, gallium is in the 4th row, and every row is a new shell. Okay, so you can see that because, hey, if boron, let's make sure I get this here, is in the 2nd shell, you can see that there's 2 numbers. The 2 is the number is electrons in the 1st shell, and the 3 is the number of electrons in the 2nd shell. Notice in aluminum, there are 3 sets of numbers. The 2 is the 1st shell, right? And the 8 represents the electrons in the 2nd shell, right? So the 8 here, and the 3 here, of course, is the valence electrons. That's in the 3rd shell. Notice the boron's outermost electrons, there's only 2 numbers in the 2nd shell. Notice gallium. The 3 is in the 4th, the outermost electron. Look at indium. The 3, the outermost electrons, is in the 5th shell, or in the 5th set of numbers. So what's different about gallium and indium? Well, they have the same valence electrons, same chemical activity, but gallium outermost electrons are in the 4th shell. Indium is in the 5th shell. And therefore, indium is going to be a bigger radius than gallium. As you go down the periodic table, you get bigger because you're putting electrons in a shell farther away. As you add more shells, the atom gets bigger. You have to know that. So going down the periodic table, indium is the bigger of the 2 because it's below. It has electrons that are filling, or the outermost electrons are in the 5th shell, where gallium only has them in the 4th. And new additional shells are always farther than the previous. Okay, so let's get back to our booklet and answer the question. Okay, again, just reminding ourselves what we have to answer in terms of electron shells. That's what the question is about. Why the radius of indium is greater, they told it was greater, than that of gallium. Well, indium has electrons that are filling the 5th shell, where gallium only has electrons in the 4th shell. It's as simple as that. Let's go to the booklet. It said indium has electrons in 5 shells, while gallium has electrons occupying only 4 shells. You could just say simply that indium has more shells. Okay, so, and you need to know that the more shells of electrons, the bigger you are. So as you go down every group, the atom gets bigger, becomes more metallic. Electrons are held farther away, easy to remove. Some things you should already know. On to number 70. So number 70, determine, again, I'm going to go right to the question. I'm going to just not look at the blurb. Determine the percent composition by mass of nitrogen. Okay, so percent by mass. If you get lost in the sauce here in terms of what do I have to do here, percent composition. Percent is always the same thing. It's part over total times 100. That's all it is. Now, to find the percent by mass of something, it's always easy to start with 1 mole of a sample. We know its mass. And we can add it up on the periodic table, or they can give it to us. And look what they did here. They gave it to us. So we know the total of 1 mole of HNO3. So we already have almost all of this done. So we know that if I plug this in, I have 63.0. It's a total mass of 1 mole. Now, if I have 1 mole of HNO3, remember, they want the percent by mass of some part, and they're telling me they want nitrogen. So in one of these formulas, how many nitrogens do you have? Well, you got 1. And in 1 mole of HNO3, you've got 1 N. They told us the mass of the total. Let's go find the mass of 1 N. You go to the periodic table, the atomic mass is 14. I know it's silly, but I just do it anyway. 1 times 14, because it's one of them, is 14. So that's the part. So in one of these formulas, the mass is 63 if you have a mole of them. If you have a mole of them, then 14 grams out of the 63 is due to the nitrogen, and you times it by 100. And we can do our math here. They didn't say set the problem up, they just wanted the answer. So you take your 14 and you divide it by 63, and then you times it by 100, and you get 22.2%. And you don't need to worry about rounding. And that's your answer. But you know what? You can't write it in the test book. In the test, you have to go in the test booklet. So let's write it in there. Notice they did not need the work here. They just want the answer. Just be careful you don't leave answers in your test. Put them in the test booklet. Person walking around should be able to check that. All right, so all they wanted was the number. So a pretty straightforward question. Now you see this, so I just don't remember how to do that percent by mass. Is there some kind of clue? Yes, there's table T. All right, so let's go there just to remind you that there's a place to look to remind you. So all of our math formulas are here, and look at percent composition. Part over total times 100. You just had to know the mass of the whole. We're going to do the mass of the mole, right? That's the formula mass would be down here. And then we had to figure out that part. What part of the formula we were talking about, it was the nitrogen. So, you could have worked that out for sure. And again, very common math problem. So again, the more questions you see, the more easy to recognize these. Number 71, balance the equation in your answer booklet using the smallest whole number coefficients. So they're telling you that you're going to make sure you round to the least whole number. Okay, so let's go to the answer booklet and do our little puzzle of balancing, because that's what it is. All right, so it's definitely a puzzle for sure, but you're trying to balance and have the same number of atoms and type on both sides. This is conservation of mass, right? So you can't have more nitrogens or hydrogens and oxygen on one side or the other. The mass on the reactant side in front of the arrow has to equal the mass behind the arrow. So many ways to start, so I'll just go left to right here. So when I look at this, okay, I see that I have 3 hydrogens on the reactant side. Now you should know the reactant side in front of the arrow. That's what I'm trying to say. And there has to be the same number. Now notice I have 2 hydrogens because of that little 2 there. So what I'm going to do, okay, is I'm going to zoom in a little bit here if I can, and I'm going to balance those H's. And I know 3 and 2 is never going to balance even whole numbers, so I need a least common factor. And I know they both go into 6. So to get 6 hydrogens on both sides, remember, I'm trying to match the number of H's on the reactant side. So to get 6 H's on both sides, okay, and I may have to change this, but it's my starting point. I'm going to put a 2 in front. Now, why do I do that? I put a 2 in front because 2 times 3 is 6. And then I'm going to put a 3 in front. Why do I do this? Because 3 times 2, okay, is 6. So I have 6 hydrogens on both sides. And let's get rid of some of this stuff as it might get confusing. Okay, now I've balanced the hydrogens, but that doesn't mean I've balanced anything else. I'm not done. Okay, now just again, it's a puzzle, and you can start and finish puzzles different ways, but I notice that I now have 2 nitrogen atoms because of that coefficient of 2 in front. And I see here that I only have 1 N. There's no nitrogens here, so I'm going to put a 2 there. And again, this might have to be fixed later, but that's how my thinking is going. So I've balanced, okay, the H's, and I've balanced the N's. There's 2 N's on both sides, and you don't have to write what I'm doing here. I'm just trying to emphasize the fact that the same number and same type are on both sides. Now, let's check our oxygens, okay? I needed to put a 3 here to balance my H's. So I've got 3 oxygens because of that coefficient. I needed to put a 2 here to balance my nitrogens. Okay, so that now I have 2 oxygens. So the total number of oxygens on the reactant side is 5. Okay, now I've got myself in a quagmire here because if you look carefully, I've got an oxygen here. Okay, and I have a 2 there. Anything times 2 in a whole number? No, it doesn't. Okay, so this is a little bit challenging. So I'm going to cheat a little bit. What times 2? Remember, there's 2 H's here, so I'm going to put a coefficient in front. What times 2 gives me 5? right? There's got to be a number times 2, even if it's not a whole number, right? And you probably guessed it, it's 2.5, right? 2.5 times 2 is 5. So to get 5 oxygens, okay, I would need a 2.5. Now you know that, if you remember from the question, I can't do this. Okay, I can't leave it like this, but there's a reason why I'm going to do this. So 2.5, because 2.5 times 2 gives me 5 oxygens. All right. Well, you know that that's going to be some issues because I can't, they said the lowest whole number and I got 2.5. But what I've done so far, my friends, is I found a ratio. And what I can do from this point is I can get the lowest whole number by doing what to this number here? Okay, what can I do to 2.5? Couldn't I times that by 2? I sure could. And in fact, to times that by 2 to get 5, I'd have to times everything by 2, right? This is really an equation if you think about it mathematically. So if I do the same thing to all of them, okay, it can be equivalent. So I want to multiply by 2, and that will give me 4. That will give me the 5. That will give me the 4. And that will give me the 6. And that's how I thought about doing this. We certainly could do this other ways, all right? But that's certainly one way to do that. I do believe that if you didn't go and do this the same way I did it, that you could have worked this out by a little bit of trial and error, okay? Because it has to balance. But I found a ratio that worked, even though I used a number that wasn't a whole number, but then I created the whole number by multiplying by 2. So that's how I have attacked this problem. All right, so on to number 72. Number 72, show a numerical setup for calculating the gram formula mass of NO2 produced. So the gram formula mass, okay, the gram formula mass, I think I meant to have the highlighter there, that's why I crossed it out. Okay, so the gram formula mass, all right, is the mass of the formula. Okay, and let's kind of erase that because we're kind of erasing the formula. So I want the formula. Let's see if I can get the, there we go, the gram formula mass, the mass of the formula. Now that it's the mass per 1 mole. You just add up all the atoms' atomic masses. You've been there before. By the way, if you were with me with question 70, they gave us this number, but they didn't have to. When they did a percent by mass of HNO3, we could have added up all the H's, which is 1, all the N's, 14, and 3 times 16, which is the atomic mass of oxygen, and we would have gotten, okay, this 63 there, okay, but they gave it to us. So here's a question where they just want you to add them up, so let's get after it. Okay, so there's NO2, and there's 1 N, so I do 1 N, 1 times the atomic mass of N is 14. I'm getting that from the periodic table. Right, if I look up N, I will see that its top number is the mass number. It has a decimal place. I'm going to round that off. Okay, it has a proton number, or atomic number of 7. That's not what I'm after. I'm after the mass. Okay, so if I do my 1 times tables, that's 14. I think I can handle that. Then I have 2 oxygens, and the atomic mass 2 times, because there's 2 of them, there's twice the number of oxygens, or in 1 mole of these particles, there's 2 moles of oxygen. So 2 times the atomic mass, and that's going to round off to 16. If you look up oxygen, atomic mass, atomic number of 8, but its mass will round off to 16. So 2 times 16 is 32. And we add them together. You have a calculator. You don't have to do this by hand like I'm doing because I'll probably make a mistake. It's 46, and that's grams per mole. All right, why I chose the lower right-hand corner to do that is beyond me. Okay, so 46 is the number you want. Let's go to the answer booklet. So if you're screaming at me because I went to get the number, I realized that they just wanted a numerical setup, my friends. So, my gosh, what would they accept? This is pretty advanced stuff, I think. I don't think so. But they would, honestly, all you need to do is take 14 plus 32. That's all they would want. I didn't see they want a numerical setup. And if you miss that, and you've got to make sure that you do. It's a good idea to do the work, even though I'm doing the work next to the problem. Obviously I can't put the answer booklet alongside this question, so I'm kind of sometimes doing the work. So it's really a good idea, unlike myself, to do the actual work in the answer booklet, so that if I was to do this in the answer booklet right here, you would still get this right because I'm adding these together and there's my work. I didn't need the answer here. Okay, so yes, don't be me, be better than me and read more carefully and look for the numerical setup. So we're putting that in the answer booklet. Did the work for NO2. I actually solved for it. They won't take off for solving for it, but all I needed was to show that I was just adding these two numbers, okay? And many ways to show that, all right? But bottom line is you're adding up the atomic masses, okay? Some people would show 14 plus 16 plus 16, right? Because there's two oxygens. All right, and that would certainly suffice as well. So many ways to do the same thing. Okay, so on to number 73. Number 73, determine the number of moles of oxygen required to completely react with 4 moles of NO. Your teacher may call this the stoichiometry problem, the mole-to-mole problem. It's a mole-to-mole problem, and it's always given with a balanced reaction. Okay, so anytime they're asking for the moles of something from the moles of another chemical, you need the balanced chemical reaction to do that. All right, so I'm going to show you how your teacher may ask for it. I'm going to show you how the easiest way to solve for this. Okay, so if you look at the question, number 73, they want the moles of oxygen, okay, in equation 2. So we're after equation 2. And they want the number of moles of oxygen. So they're after O2 here. And they gave you 4.0 moles of NO. 4.0 moles. So I'm going to get up close and personal here. So what your teacher probably taught you was you take the moles given, and that'd be 4.0 moles of NO. And what you're going to do is get rid of NO. So you're going to put NO on the bottom, and you're going to get O2. And we're going to put in the what? The mole ratios. It's a 2-to-1 ratio. So there are 2 NOs to 1. You need the balance coefficients. Those are called the mole ratios. So I'm getting that. Nothing in front implies 1, right? So make sure you understand that. And of course it's a 2 here, and of course that goes there. So you notice the reason why I put NO on the bottom, because it will cancel. It's a way we do conversions. So 4 times 1 is what? 4 divided by 2, and you're going to get 2 moles of O2, because that's the math ends up that way, and you're left with the unit. The only unit left standing is O2. And if you look at the ratio, it's a 2-to-1 ratio. So if you have 4 moles, what's the X going to be? It's going to be half that. Okay, now I did promise that I'd do it another way because some people don't like that. This is an easy problem, and again I just want to make sure I have it right because sometimes I read these incorrectly. So it's 4 moles of NO to oxygen. Okay, so yeah, we did that right. Equation 2. So I'm just going to do this again. Okay, and you can decide which way you'd like. If you can connect with the first way, that's the way that I'd love you to know it, but I just at this point want you to get this right. So let's change colors here. And so we have 4 moles. We're asking how much O2 do we need to completely react with 4 moles here. So I'm going to make a proportion, and my line is going to be right through the chemical formulas. And the coefficient becomes the denominator. Nothing in front implies 1. So what do I have? I have, if I can rewrite this, if you can't see it, it's 4 over 2 equals X over 1. That's what I have here. And of course you can cross multiply. You're going to get 2x, right? You're going to get 2x cross multiply. 2x equals 4. Solve for x, divide by 2, and you're going to get 2 again. Same idea, right? So to get rid of this 2, we divide by 2, and you're going to get 2 moles. And that's your answer. Okay, so a couple different ways to do it, but again, recognition is the key. What kind of problem is this? This was a problem, and it's a typical math problem where we want the moles of one compound needed to completely react with the moles of another compound. And we're going to use the what? The mole ratios in a balanced chemical equation. So this is the mole-to-mole problem. All right, so the answer is 2. We're going to put that in the answer booklet because it's fun. 2, 2.0 if you're into the sig figs. They're not really, you know, they're not asking for any sig figs or really units, even though in this case they gave you the units. So 2 is the answer. Okay, simple problem. Again, the identification is the key. That's why you've got to practice. 74. Going to go right to the question. Leave the blurb alone, see if I need it. State the molecular polarity. This is the polarity of the molecule, not the bond. Okay? Anytime you hear the word polarity, polar, are we talking about the bonds between atoms or the polarity of the entire molecule? If you don't know that distinction, you're in trouble here. But they want the polarity of the entire molecule. Okay, for each of the reactants. Well, my friends, you have to know that this is the reactant side. Okay, and we're making glucose and CO2. This is photosynthesis. Okay, but does not matter. They want to know who's polar, who's not, possibly. So let's look at CO2. CO2, the Lewis structure would be like this with 2 lone pairs. Oh my gosh, you can memorize these. They're the same chemicals over and over again. So CO2, because it's symmetrical, okay, it's nonpolar. If you are symmetrical, there's no difference from one side to another. So you can't have poles. You can't have any differences. Okay? Now, if you look at water, we'll do it in different color. You should all know that water is polar. You have to know this, but it's polar because it's a bent molecule. The Lewis dot structure, these 2 lone pairs, okay, bend downward, bend down these pairs of electrons in the bond into a bent shape. Water is asymmetrical. It's got differences. The O has a different side than the H, and because O is electrically more electronegative than hydrogen, it pulls more electrons near it. This is the negative end, this is the positive end. Water is polar. Why is it polar? It's asymmetrical. There are differences. If you draw this and cut this out, you can see that O is different from the H end. Okay, this one is symmetrical. So you got to just know these shapes. A couple of other ones they always pick upon, even though it's not part of the problem. Ammonia. Nitrogen has 5 valence electrons. So H brings another one to the table. And we have the octate for N, but this is not the same all the way around. So ammonia is also asymmetrical. Therefore, it's also polar. How about methane? Okay, dashes are pairs of electrons. That's the same all the way around. That is symmetrical. There's no different side to it, so there's no poles, there's no differences. So it's also nonpolar. Okay, so they pick on these same chemicals all the time. All right. If you forgot that CO2 was linear, I could go slower with you a little bit here. So let's do carbon. It has 4 valence electrons. Oxygen has 8. I'm going to do oxygen with red. I'm always going to start with a bond. 1, 2, 3, 4, 5, and 6. Another oxygen has 1, 2, 3, 4, 5, and 6. And it looks kind of weird right now because it is not correct. If I look with oxygen, it feels like it has 7. If you count the electrons, it's only sharing 1 more. And this oxygen has the same issue. And carbon feels like it's only sharing 6. So this is not working. They want to feel like they have the octet. So that's my check. So I'm going to get rid of the circles. And all I can do now, party people, is I can move these dots. Let's make another bond. Oh yeah, move this guy over here. I'm feeling kind of magical moving these around. Move this one around. Oh, Christmas made it too small, but just want to move it. Oh, okay. It's not moving. So I'm just going to erase it because that experiment is over. And we're going to put a dot here. And if we just check, party people, hey, this guy feels like it has 8. And oxygen, by sharing, feels like it does so. So we do the same thing on the other side. Get rid of this dot. Put it here. That's a black. And then we're going to get rid of this red dot and do the same thing. Make sure they're the same color. I can do this. And oxygen, even though I have this kind of ugly, these two, maybe I can move these today. Yep. Okay, so you can see that we've got our double bonds. Every bond is a pair of electrons. But more importantly, if we check out the carbon, it also feels like it has 8. All right, so that's kind of how I do the Lewis dot diagrams. But why do I know it's linear? I know it's linear because there's no lone pairs of electrons unbonded above or below the carbon to bend these into any shape. If you look at the one water I drew, even though I didn't draw that kind of nice, but these two lone pairs, and you say, well, how do you know it's lone pairs? Oxygen has 1, 2, 3, 4, 5, and 6. Hydrogen brings 1 to the table. And you can see that now what? Oxygen feels like it has an 8 by sharing. But these two lone pairs in the central atom are going to repel downward these electrons into a bent shape. And same thing here. With nitrogen, this lone pair is going to bend these electrons down to an asymmetrical shape. Okay, so that's how you know that if you're stuck. But you can memorize these because they're the same chemicals over and over again. So bottom line is CO2 is nonpolar. You should know why. It is symmetrical. And water is polar for things that you should already know. Water, because we're living, is polar. Okay, so CO2 is a nonpolar molecule and water is a polar molecule. Okay, you should know that no matter what. Okay, any case, on to number 75. Could you just put nonpolar and polar in those spots? Absolutely, we'd take it for sure. So on to number 75. Number 75. In the space in your answer booklet, draw a Lewis electron dot diagram for a molecule of water. Oh gosh, if you're with me with 74, we kind of did that, but let's go there and draw the Lewis dot diagram for water. So I start with oxygen. It's got 6 valence electrons. How do I know? If I go to the periodic table, atomic number, 8? Its mass is 16. Underneath it, it's going to say 2-6. So it's got 6 valence electrons. Now I know it's going to bond with 2 H's because we're trying to do it for water. So I'm going to put 1 electron out for the H and the other electron out for the other H, and I'm left with, 4 more. I'm going to pair them up. Now, you don't have to do it like that, but you definitely have to put out 6 valence electrons. And then the hydrogen, it has 1 valence electron. Why? Because hydrogen has a mass of 1, atomic number 1, and of course it just has 1 electron, so its configuration is 1. And that'd be fine. You could also have done it like this. Have an O, and some people put the 2 lone pairs here. Right. This is troubling because you could think that water might be linear, but totally acceptable as well. Okay, you could use sticks for the bonds. Okay, so you could say oxygen. Okay, there's a bond to the hydrogen. Remember, a bond is a pair of electrons, and then the 2 lone pairs. So many ways to skin a cat. I do navel up. Do you have to show it in a bent form? No, you don't. Okay, all right, so on to number 76. Number 76, based on table S. They're telling us how they want us to answer the question, and they're being nice by telling us to go there. Compare the strength of the attraction of a carbon atom for electrons with the strength of attraction of an oxygen atom for electrons. You need to know that the attraction for electrons, you need to know that is, my friends, electronegativity. And that's something that comes up in the multiple choice all the time, as do the rest of these questions. So what they're really asking, based on table S, okay, who has a higher electronegativity? Because electronegativity, of course, is posted. And we're comparing a carbon versus an oxygen. Okay, and I can already tell you that oxygen being farther to the right is going to have a higher electronegativity, but if you don't know, you can just look it up. You just had to know that the attraction for electrons is electronegativity. They're not saying why. They just want you to compare. Okay, very simple. So let's go to table S. So carbon versus oxygen is plain as day in front of you, unless it's nighttime. The electronegativity values, carbon is 2.6 And oxygen is 3.4, so oxygen has a higher electronegativity. Are you really kidding me with this question? You just had to know electronegativity is the attraction for electrons. By the way, what's the first ionization energy? That's the energy needed to pull an electron away. So it takes a lot more energy to pull electrons away if you what? Attract them more. So these guys always go hand in hand. And you should also know, as their radius gets smaller, your electronegativity goes up. Along, so that should make some sense. Okay, so as you get smaller going across, now I should be careful going across. Lithium is where we should start here, but you can see as the radius gets smaller, electronegativity does increase, and so does the what? Ionization energy. Get more careful there. Okay, so anyway, on to the next question, or at least let's get to the booklet. I said oxygen has a greater electronegativity than carbon. Okay, you can also say that it has a greater attraction for electrons than carbon, since that's what electronegativity is. You can also put down the actual values. I would not do that because you can make a mistake. Okay, so oxygen from table S has a greater electronegativity. Onto number 77. Number 77. State in terms of electron classification. I'm sorry, element classification. All right, I'm losing it. Element classification, losing it. Maybe I already did. Okay, why CO2 is why is it a molecular compound? Okay, so the word molecular compound, what does that mean? Now, in terms of element classification, so elements are one of three things. They're metals, nonmetals, or metalloids. So why is it a molecular compound? Now, that means a molecular compound, my friends. It means it makes molecules. CO2 is a molecule. That's a particle. As I've drawn before, it's one C bonded to, double bonded to two oxygens on either side, but that's the particle. Okay? Who makes these types of particles where they don't just keep repeating over and over again? It's the nonmetals bonded to nonmetals, so a molecular compound is something that has covalent bonds, but it's always between nonmetals and nonmetals. If it's a nonmetal and a metal, case in point like sodium chloride, table salt, that's ionic. That is not going to be a molecular compound, because really what this is Na plus attracting a Cl negative, and that's actually in a crystal lattice that keeps repeating. Na plus attracts Cl negative, negative. This attracts an Na plus. This, of course, ionically attracts the Cl negative, and this crystal goes on. Okay, not a great three-dimensional crystal, but this goes on. So ionic compounds do not make molecules, they make crystal lattices. They're solids at room temperature. Whereas molecular compounds actually make molecules, a particle that has a finite, an exact number of elements that are involved in it. In this case, there are 3 atoms only in CO2. When we say the compound sodium chloride, there's a huge number of sodium chlorides in that crystal. We just give the lowest ratio of the ions in a crystal. And if something is a metallic compound, that'd be metal and metal. Like sodium, solid, implies that sodium atoms are bonded to sodium atoms some huge number of times, also in a crystal where the electrons are free to move. We say the sea of mobile electrons. So be aware of that. So in terms of element classification, the reason why CO2 is a molecular compound, because it's made up of nonmetals bonding to nonmetals. Okay? And that's not the case for ionic or metallic bonding. Okay? Or those classifications. So only nonmetals involved, you have to be a molecule. You're going to share electrons until everybody has its octet, or close, or something like the octet for hydrogen, which would be 2. Onto the booklet. Carbon and oxygen are nonmetals. That's it. Okay? Now, they didn't really ask for why. They just said, really, in terms of element classification, carbon and oxygen are nonmetals, and therefore all nonmetals bonded to each other are covalently bonded, and they always make molecules, or they're called molecular compounds. You can write all that, but we would take carbon and oxygen are nonmetals. That's the classification. Okay, so on to number 78. Number 78. Write the empirical formula for glucose. That's the lowest ratio, my friends. There's a molecular formula, which is the actual ratio of things bonded covalently. How many is needed to make the octet for all the atoms, and 2 for hydrogen. But the empirical formula is just the lowest ratio. So take glucose, which we know is C6, H12, O6, reduce it, and it's going to be CH2O. I mean, we've seen this problem, and they use glucose all over the time. So people like 78, they just wanted to give you an easy problem. But if you don't know the empirical formula at this point, man, I don't know what you're doing. Lowest ratio, make sure you know that for the next time, the lowest ratio. Now, some molecules are already in their lowest ratio. So like water, H2O, okay, that is its molecular formula. That's how it exists in nature, but it's also its empirical formula. But hydrogen peroxide, H2O2, that's the actual bonding ratio of those atoms in that molecule, but its lowest ratio is HO. Okay, so in any case, let's go to the booklet. So it's a 1 to 2 to 1 ratio, so CH2O, that's the formula. You could actually put them in any order too. We would take that as well. All right, so on to number 79. Number 79, state the class of organic compound to which the product in the equation belongs. Well, this is the product. After the arrow, we have products. Before the arrow, we have reactants. So what class is this? Well, I look at this, I see, oh, this is organic chemistry. I see carbons. To be organic, you have to have carbons. But I see an OH group attached to a carbon chain. To know what kind of class, I need to go to table R. It's just that simple, if you don't know this off the top of your head. So let's go there. And they give you the general formula. Remember, here's a class of compounds, and we have an OH group attached to an R. That's the general. The R is the rest of the organic compound, kind of like an example they give you. They give you the rest of the carbons, and then there's an OH attached to it. So this is clearly an alcohol. That's all you had to do, guys. Okay? And alcohols are not bases because these are covalently bonded. They're not metals that are ionically attracted or bonded to the hydroxide ion that comes off. These are not hydroxide ions that come off. These are bonded covalently. So in any case, this is an alcohol. It's just simple as that. I mean, they're just trying to give you points there. Alcohol or alcohols work. So on to number 80. So number 80, state in terms of carbon-to-carbon bonds. They're asking you to answer the question based upon carbon-to-carbon bonds. If you don't answer it based upon this way, you will not get it right. Why the hydrocarbon is unsaturated. And unsaturated means you're under the maximum amount of H's possible. So what I mean by that is, so why the hydrocarbon? You say, oh my God, which one is the hydrocarbon? Which one is there only hydrogen and carbon? Hello? Right here. So they wanted the hydrocarbon. You have to read carefully. Okay? So why is it unsaturated? It's unsaturated because if I only had one bond, right? Let me take one away. I know that carbon makes 4 bonds. Or can make 4 bonds because it does always make 4 bonds because it has 4 valence electrons. So this wouldn't work. So it would need one more H here. Okay, however we want to put the H here. So each one would have, and it kind of looks kind of sloppy, but it'd be CH3 on one side, right, if I do it this way. And then CH3 here. The dashes, of course, are H's. So if it has a single bond, it has room to have more H's and be what? Saturated, filled up. To be saturated means to have a single bond. But if I've got a double bond, my friends, in chemistry, I can't make 5 bonds. I only got room for now, because there's 2 what? Bonds in between the carbon, and each carbon must make 4. I've only got room for 2 more bonds because of my double bond with the carbon, because carbon must make 4 bonds. So back to the question, state in terms of carbon-to-carbon bonds why the hydrocarbon is unsaturated. It's unsaturated because of its double bonds. It has multiple carbon-to-carbon bonds, which really means it can't hold on to the max amount of H's and be saturated. You should know that alkanes are single bond, they're saturated. Double bonds, alkenes, And triple bonds, alkynes, are the unsaturated ones. Table Q can help you with that. So it's about the idea that it's unsaturated because it has a multiple carbon-to-carbon bond. Okay, let's get to the booklet. Ways to answer this, but there is a double bond between the carbons in the hydrocarbon. Okay, and you can say this so many ways, but you needed to speak to, my friends in chemistry, the type of bonds. Single bonds have room for more H's and are saturated. Okay, when you have a double or a triple bond or a multiple, you could say that the molecule has a multiple carbon-carbon bond. Same idea, so many ways to say it, but darn, it's a bottom line here. They wanted you to answer in terms of the bond between the carbons. So being unsaturated means that you have a double or a triple bond. Okay, and so we said in this case there was a double. Don't say there was a triple bond, because if you did, that'd be wrong. So a multiple carbon-to-carbon bond or a double bond would work here. On to number 81. Number 81, identify the element in the product of the reaction that allows it to be classified as an organic compound. Oh my gosh, how many times have we seen this? To be organic means you must have carbon. The organic unit starts with table P, and table P is the prefix of all the naming of organic compounds, and it all starts with how many carbons in the longest continuous chain. Meth is 1 carbon, eth is 2, so everything is surrounded by how many carbons in the parent chain, and then what's attaching to the carbons. So it's all about carbon. Into the booklet, you should have this down. This is popping up in multiple choice and very easy part 2 questions. This is a gimme. You got to get it. Go get it. Yeah, so it's carbon. Whether you write the element symbol or write it with a apostrophe like I said, carbon. Okay, that's the answer. On to number 82. Number 82, identify the liquid tested by the student that's the most acidic. Got to go into the blurb and information. What do I know? The most acidic. The way to remember pH is we're going to go from A, using our alphabet, start low, go to B, we put 7 in between. And we're going to say that going down from 7, we become more acidic. Okay. Okay, and then going up from 7, we become more basic. So, I am looking for, guess what? The lowest pH scale, the lowest number. So the liquid with the lowest number is 2.1. So lemon juice. That's the lowest pH. And you need to know that the pH drops as things get more acidic because the H plus ion concentration or the H3O plus, they're synonymous, is increasing. Case in point, if we compare a pH of 4 with a pH of 2, 2 being more acidic, here's the reasoning. Okay, pH of 4 has a concentration of these guys, the molarity of these guys, as 1 times 10 to the negative 4. That's its molarity. This got to be 1 times 10 to the negative 2. Remember, pH is the positive value of that negative exponent. Who's a bigger number? By 100 times pH of 2. So you've got more of these in a lower pH. That's how it works. So in any case, if you don't like that, just do what I did. A, do the alphabet from the bottom to the top, A to B, 7 is in the middle, and you get more acidic as you drop downward from 7. So lemon juice. Let's go to the answer booklet. So I said lemon juice. I stayed with the pattern red, blue, black, but I guess I should have went with like a yellow for lemon juice. You could say lemon too, because it comes from juice of lemons comes from lemon, right? So 82 is the answer. That's the one with the lowest pH, most acidic. On to number 83. Number 83, state the color of brome cresyl green or brome cresyl green. I've been saying cresyl all my life, and I heard a colleague of mine say cresyl, and I guess that's the way you say it. After the indicator is added to a sample of lemon juice. So we need to know what color it is, and we know it's below 7, it's 2.1. So we need to go to a table that we use to see the actual pH ranges where pH indicators change, and that'd be table M, or good. So that's where we're going to go now, table M. So brome cresyl green, okay, we noticed that the pH is 2.1, okay, for that lemon juice. And how you use this is understand that anything 3.8 and lower is going to be yellow. Anything 5.4 or greater is going to be blue. And if it's in between, the color between yellow and blue would be green. Okay, so that's how you use this. So because it's 2.1, it's way below 3.8, so it's going to be in the yellow range. Yellow goes from 3.8 all the way down to the lowest pH possible. So anything 3.8 or lower is yellow. So we put down yellow. Just that simple. To the booklet. Yeah. Anyone see what I did there? Yeah. I put it as yellow color. Okay, I broke the pattern. But yeah, it's yellow if you can't see that. Okay, so yellow is the color. Okay, based on table M. On to number 84. So number 84 says complete the equation in your answer booklet by writing the formula of the missing product in the reaction of the aqueous potassium hydroxide with vinegar, acetic acid. Understand potassium hydroxide is KOH. It's listed in the base table, table L. Okay, and notice vinegar or acetic acid is listed in table K as an acid. So we've got ourselves an acid and a base reacting to each other. But let's go to the booklet to see what the reaction is and how do we figure out the special missing product. Okay, we got our KOH, which is a base, and we've got this compound here that I know is an acid because there's an H in front. I have a hydroxide with a metal, it's a base, and like I said, these two things are listed in their tables. Let's go to the tables so you understand it's an acid and a base. This is what this question is about. Table K, here's our acetic acid, people. And it's written for us right there. And in table B, here's our KOH. So they just gave you things that we already have. So we have an acid and a base reacting. This is a neutralization reaction, acid and base, if you haven't warmed up to this. All right, so let's get to the booklet again. And so what do we know? When we have an acid reacting with a base, we should know that we're going to make water. We're going to neutralize the acid and base. We're going to make water and a salt. This doesn't look like water. Okay, this looks like a salt because I see a K in front. So my friends, it's going to be water. Okay, acid and base makes a salt and water, and I'll explain this. The answer is H2O. That's the simplest compound they can ask for. But how do they do this? Well, it's really neutralization. Acids are dangerous by themselves and so are bases, but when they react together, they neutralize themselves and they're no longer dangerous. Okay, so the way to do this, understand it, is that neutralization is kind of like a double replacement. K is +1. Hydroxides from table E are -1. Acids will break apart into an H+. That means the rest of this whole thing here is an acetate ion that's listed in table E as -1. So what we're going to do is switch partners. The K+ is going to go with this negative, and this H+ is going to go with this negative to make water. So that's how you do it. We already have the K+ hooking up with the acetate ion -1, which is listed in table E, and I'll spare you going to table E right now. Okay, so it's really it's an example of a double replacement. Even though we don't call it a double replacement, it is one. But the bottom line here is that the base, which is made of a hydroxide, is reacting with the acid, the H+, and you're making water. That's the overall net ion reaction. Okay, but it's neutralization. So you're looking at water. Okay, for all those reasons, because the hydroxide, the negative ion here, is going to hook up with this positive ion that's dissociated. And keeping with some colors here, the positive here will hook up with this negative. Okay, and that's how we make this compound. And we make this compound. You can write HOH if that helps. Okay, so in any case, acid and base is salt and water. So if you didn't like anything else, if you didn't like how I did that, you should have known that. And they really were trying to drive that home. On to number 85. 85, we did it. We got to the last question here, party people and people that don't know what the party is. Okay, so based on the pH, party is right here, of course. Based on the pH value in the table, compare the concentration. Compare the concentration. I'm underlining these things because I want you to understand what they're asking. Compare the concentration, that's the molarity, of the hydronium ions. What are hydronium ions? They are H H3O+. They're given to you in Table E. They're synonymous with H+. We should all know they come from acids. Acids create H pluses that are donated things, or they create H3O pluses when they react with water. So, okay, I'm going to compare the acid part of water to the concentration of the hydroxide ions. Again, if you don't know hydroxide, you should, but Table E shows you that's the base part. Okay, that's the hydroxide or the ion, that's the base part of the water in the distilled water. So what they're saying is in distilled water, compare these values. If you check out distilled water, it's got a pH of 7. And if you notice my chart that we did for other, and I'll rewrite it here if you weren't with me, I like to write pH like this. A starts in the bottom and follow the alphabet, so B continues. 7 is in between. As we get more acidic, okay, we get drop lower than 7. As we get more basic, we're above 7. So if we're right in the middle, these guys have to equal each other, all right? If you're below 7, you're more acidic than basic. If you're above 7, you are more basic than acidic. But if you're at 7, you're right down the middle. Many ways to think about that. Or if I have equal numbers of H plus or H3O plus and it equals hydroxide, okay, that must be a pH of 7. That's a neutral pH. Neutral because equal amounts of them will make water pure water. Okay, that was a really better answer than that. Okay, because in pure water, okay, the amount of H pluses or H3O pluses equal the hydroxide. Someone figured out the total amount of these guys. They figured in pure water there's 1 times 10 to the negative 7 amount of these guys. And someone figured out in pure water there's the exact same 1 times 10 negative 7. How do they know? Because they multiply this together and they got 1 times 10 to the negative 14. So pH became, what's the positive value or negative log of that number? So of course the pH is 7. So any case, there's more of that in a higher level course, but in your course, hey, equal amounts of OH and H plus, or you have a pH of 7 that's neutral, they're equal, okay? So that's all you need there. Number 85, last question, I hope you loved it. On to the booklet. So you would say equal. You could say the same. The amount of H3O plus equals hydroxides, okay? So they're the same, and I have this reaction here from explaining number 84. So when these guys are equal, okay, there's no more hydroxide in H+, they're equal in pure water, the pH is 7. All right, hope that helped. Good luck with the test. Okay, I hope I can show you that the part 2 isn't something very scary. It's the same concepts in the multiple choice. They're just lipstick to a pig a little bit. They just kind of dress it up a little bit. So don't be intimidated. Same concepts. I hope that helped. And good night.